Hello everyone, I Nikhil welcome you to Vigyan Bharat. We are back again with another interesting lecture. Today I am going to discuss the concept of what is an upper bound and lower bound. So let's quickly start the lecture. Let's see the outline for today's lecture. It's as follows. First we're going to discuss what is the meaning of an upper bound, and similarly for a lower bound, what it means for a non-empty subset of R to be an upper bound and a lower bound. Then we're going to see what is its geometrical interpretation, how we can interpret it geometrically. Further, we're going to discuss the notions of bounded above and bounded below. So these will be the broad outline till the end of today's lecture, and in between the lecture I'm going to cover so many good exercises, so many good examples, some good observations. So you just need to watch the video till the end to get a better clarity, and in the coming lecture I'm going to discuss the most important concepts from where so many problems come to the exam, like of suprema, infima and similar stuff. So without any delay, let's start our lecture. Also, I'm going to discuss some of the important exercises, PYQs from CSIR net and related exams. So let's begin. First, we're going to discuss what you mean by an upper bound. Whenever I'm defining the notion of upper bound or a lower bound, I'm going to define in context of some non-empty subset of the set of real numbers. So here I assume that suppose I have a set A, of course non-empty, then I say that this set A is said to have an upper bound, where upper bound is a real number. What upper bound is a real number. If you can understand this situation, what's happening here, try to see this figure. You see these gray ones from here till here. The gray elements represents the elements of the set A. Now what is my task in order to find an upper bound? What I'm searching for an element on the real line, because here all the elements of the set A lie on the real line. So I'm searching for an element, I'm searching for a real number which is greater than or equal to the element of all the elements of the set of given set. Let me repeat what I mean to say. We say what I'm searching for a number such that all the elements of my set are less than or equal to that number. So if you see this figure here, this quantity alpha, this element alpha, which is of course a real number, lies to the right of all these elements as well as these elements, which I'm calling by my x. So these are my possibilities for x, all the gray elements. Now this alpha satisfy condition that it always, that is what it satisfy, all the elements of the set capital A, which I denote by small x, all the elements of the set A are less than or equal to this alpha. That is, either they are smaller than alpha or at max they can be equal to alpha. There are two conditions. What it means, x is less than or equal to alpha. So it has to satisfy either means any one of the, if it satisfies any one of the property, then in that case I say that this alpha, this real number alpha, is an upper bound for my given non-empty set A. Fine. So let's now see what I have already even told you. Let's now try to move ahead with the geometrical interpretation clearly, and further we're going to see its mathematical definition. Okay, so let's see. Here what I have written, try to just read this. All the element of my set A lies to the left of alpha on the real number line. That is, in that case, I say this alpha is a upper bound for my non-empty set A. Here what I have written in terms of quantifiers, that is, for every x belongs to A, x satisfies this condition that x is always less than or equal to alpha, that is, it always lies on the left. So let's move ahead and see what's the then definition by this intuition. What will be the definition for an upper bound of a non-empty subset A of R. So this is the definition then. Here I have given this information that A is some non-empty subset of R and alpha is a real number. Then alpha is said to be an upper bound of my set A if for each x in A, that is if for every element small x belong to the set capital A, we have this condition, that is x is less than or equal to alpha. So in that case we say that alpha is an upper bound for the set A. I hope it's clear. Let's now move ahead in terms of quantifiers. What I have already told you, that alpha is an upper bound of A if for every element small x belong to the set capital A, there exists this alpha. We are calling this upper bound if alpha satisfies this condition, that is alpha is greater than or equal to x for every x in the set A. In that case I say that my alpha is an upper bound. Let's look at some examples, and I noted by one because I'll be making some observations later, so that's why I have given it as equation 1. Let's try to see first example what it says. Let's suppose my A is the collection of those real numbers which lie between -1 and 1, including -1. 1 is not included. So that is all those real numbers which are greater than or equal to -1 and strictly less than 1. See here I have the equality greater than or equal to 1. If I break this inequality, I can write it like this: x is greater than or equal to -1 and x is less than 1. So I'm collecting all those real numbers which lie, if I can rewrite it, it is nothing but this semi-closed interval, this one. Fine. Then A is precisely this, which what I have just overwritten. This is my A. Another way to write it. Then I say that I have to now, I'm looking for an upper bound for this set. So I have to find an element such that all the elements of this semi-open interval, a semi-closed interval, are less than or equal to that number. So if you see here, there exists a 1. In the set of real number line, there exists a 1 in R such that x is less than or equal to 1 for every x belong to this interval. Of course, if you see, you observe that the equality will not hold because 1 is not an element of this set A, which I have expressed in terms of interval. So, but it satisfies that property that all the elements of this set will be less than or equal to 1. Of course, they are strictly less than 1, so they satisfy this condition here. So in this case, I say that 1 is an upper bound. 1 becomes an upper bound of A. Is it clear? I think. Feel free to ask if you have any doubts in the comment box later. Okay, now I have asked you, let's see the negation of 1. Negation means just the opposite of what we have just written in 1. In 1, I have written that alpha is an upper bound of A if they satisfy all this property. Now I'm looking for the opposite. That is, I'm looking when alpha is not an upper bound of A. So what will happen if alpha is not an upper bound of A? See, think. If alpha is not an upper bound of A, then I'm able to find at least one element in my set such that the element is greater than that alpha. If that happens, that in that case I say that alpha is not an upper bound, because previously alpha or every element of the set was less than or equal to alpha. Now I am saying alpha is not an upper bound, so there exists at least one element small x in the set A which is greater than alpha. I hope this is clear to you. Let's move ahead. So how this will look? This will look like this. Now see, the small x or all the gray portion, this gray one, from here to here as well as from here to here, all these gray points on the real line represent my set A. Here is my set A, all these gray elements. So I'm saying alpha is not an upper bound, but I'm saying alpha is not an upper bound of A. You can easily see that I'm able to find at least one x, although there are like more than one, even To be very precise, there are infinitely many, but I have find this one, this guy. If you like this guy, this x is greater than alpha, or alpha is less than x. So previous condition is not satisfied now. I have found an element which is greater than that real number. So in this case, alpha is not an upper bound of the set A. Let's move ahead now to the lecture. Now here are some observations which I want to make. Suppose you go back to the first figure which in the very starting which we have taken. Now if suppose there was some another guy which lies over to the right of alpha, let me call it some, say, beta. You can give it any name, it's a dummy variable, it's dummy, name is dummy, you can give it anything. So suppose I call it beta. Now whatever the property which my elements x of the set A was satisfying in respect of alpha, they will still satisfy in respect of beta, because here every element of my set, if you look here intuitively, geometrically, they are less than alpha. So of course they are less than beta also, because beta is greater than alpha. So if alpha was an upper bound for the given set, so in that case I can say if any number larger than alpha will also be an upper bound for my original set. So in this case I can say that beta is also an upper bound. So this was the next result which I'm going to explain now. Try to see this observation, that suppose if alpha is an upper bound of A, that is this information is given. This information from here till here, this information is given to us that alpha is an upper bound of A. And further, what I'm saying, that suppose there exists, I'm choosing some real number alpha prime which is greater than alpha, then in that case this alpha prime also becomes an upper bound of my set A, which you can see it geometrically. It's quite clear from the explanation given above. Okay, and even further you can say any number, suppose I took another number, say alpha double prime, so it is greater than alpha, of course greater than alpha prime, so it also be an upper bound. Any number greater than that will also work. Let's move ahead. That whatever I have just explained, I have just written it, that if we choose a number greater than alpha, then that number will also be an upper bound for the original set. You can construct many examples based on your understanding. This is an exercise which I expect now from you, that you can define on the similar lines what you mean by lower bound, what we mean, suppose alpha is a lower bound, then you have to find where the geometrical interpretation, basically A part asks for the geometrical interpretation where the elements of my set A lies, when we say that the number alpha is not a lower bound, and finally express all the things in terms of quantifiers. So this is the first exercise of the lecture. Try to attempt this on a similar lines, how we have defined for an upper bound. Just I will give you a hint what will happen. The sign of the inequalities will reverse. The sign of the inequality will reverse, and you can easily generate the definition yourself. If you have any doubt anywhere, feel free to ask me in the comment box or in the Telegram group. Let's move ahead. Let's see an example now. What it says. Now I'm considering the set of natural numbers, that is a counting numbers. So it is given here. This is my set. Now I want you just think, before looking down the explanation, just think on the real line. I have 1, 2, 3 and so on. I have these infinitely many natural numbers. If I look to the left of 1, I can find any real number which is smaller than 1, and that will work as a lower bound for me, because it will be less than all the elements of my set. That is the definition of a lower bound. So I have chosen 0 here, but I have chosen 0. On the real line, 0 lies to the left of 1. So it is smaller than every natural number. So 0 is a lower bound. Of course, if you choose another number which is less than 1, that will also work as a lower bound. So I have to just in particular chosen that I have observed that 0 belongs to R, such that this condition is satisfied. This is the condition for a lower bound. That is, x is greater than or equal to 0 for every x belongs to a set of natural number. Every element of my set is greater than or equal to 0. Of course, they are greater than 0, so it satisfies this relation, greater than or equal to. You can another way write it like this. Okay. So from here you can see that 0 is a lower bound for the set of natural numbers. Now I have posed a question to you. Try to answer me, although I have given a good justification to it, that whether is this 0 unique, whatever the 0 we have found, is this 0 a unique lower bound? That you have to answer to me. Or does the set of natural numbers has any other lower bound? So try to answer me in the comment box. Let's move ahead to the next, now into lecture. Now there are some interesting questions which we should think ourselves. Does the set of natural numbers has an upper bound? That is, will there be any real number such that all the elements of the set of natural number will be less than or equal to that real number? Can I find a real number? So try to think it and answer me again in the Telegram group or wherever, like in the comment box. Obviously it's a very simple question, you can think it yourself, because I give you just a small hint and indication that set of natural numbers is an infinite set. The set of natural numbers is an infinite set. If you can find a real number, if we assume, suppose there is a real number such that all the elements of the set of natural number are less than or equal to that real number, if I add 1 to that real number, can I find some number close enough, maybe some natural number which is maybe greater than the previous real number which we choose? Try to think it and answer me. Now here comes the most important exercises for the today's lecture. Whatever you have just understood the meaning of a upper bound, a lower bound, in that context you have to solve each of these 7 exercises, A, B, C till G. These are the exercises. I just going to discuss and give you hint for some few of them. They are very good exercises. Like, see the first exercise itself. Here what we are considering, all the non-negative real numbers. Greater than equal to 0 means non-negative. So you see here, is there a lower bound for this set? Which you can see, of course, you can see a plot on the real line. You can see there exists 0. There exists a real number 0 which satisfies this condition. 0 is less than equal to x for every x in the set A. So 0 is a lower bound. Is 0 unique? No. You can find some number, real number, which is less than 0, and it will also work as a lower bound. So this set has many lower bounds. Of course, infinitely many. Now, this B is interesting question in the case B. Now I have asked you this infinite open interval minus infinity to infinity, or the set of or my real number line complete, whether it possesses any upper bound or lower bound. Trying to answer me. Similarly, this is a good problem. In C, that you are considering all those fractions of the form P by Q, where P and Q are both positive. This is important. They both are positive integers. So does they possess any lower bound or any upper bound? So try to answer me. This is a very important exercise, this E. Consider the open interval -1 to 1 and union singleton set 0. Likewise. So you have to attend all the exercises. This G exercise is the interesting exercise. I would say it's an important exercise. This G is interesting. Try to approach this exercise through a different perspective. Try to plot this. If you can plot this and what are the possible values which you are getting, from there you can easily get what are your upper bounds, what are your lower bounds. So try to solve each of the above exercises. They are very good exercises. So we have covered like half our lecture today. Now we're going to begin the second half of our lecture. What we have learned till now, what is an upper bound, what is a lower bound, which you have to define and left it over you. On the similar lines, just reverse the sign of inequality. We have seen some examples, and finally you have to do those exercises. Now we are moving ahead with the concept of bounded above. When we say a set is to be bounded above, let me explain you intuitively. If suppose I have a non-empty set A of real numbers, then I say that that set is bounded above if I can find an upper bound for the set. If I am able to find an upper bound for that set, in that case I say that my original set A is bounded above by that upper bound, say alpha. So alpha is an upper bound of A. Then in that case I say that my set A is bounded above by alpha. Of course, it has to be real number. You can read the definition, it's quite simple now. Let A be a non-empty subset of R, then A is said to be bounded above. Bounded above where? In the set of real numbers. Your subset is defined in whose context? The greatest set which we have in this reference is this A is a subset of the set of real numbers. So we say that A is bounded above in R on the real line, when it will be bounded above if there exists alpha in R, which is an upper bound of A, that I have explained. That is, all the elements of set A has to satisfy this condition. In that case, I will say that my A is bounded above. Okay, so on the similar lines, you can easily define what we mean for a set to be bounded below. Just the sign of the inequality will reverse. Then that real number will be alpha. If I say again, the alpha is a lower bound for my set if alpha is less than or equal to x for every x in that set. Okay, let's now see an example. Quite good example this is. Okay, let me just change the color just a second. Okay, perfect. Okay, let's see this example now. Consider this open interval from 0 to 1. Now again we have to find an upper bound and lower bound for this set. It's pretty easy now. It's an easy exercise. If you visualize this interval on the real line, you see that all the elements of the set are less than 1, strictly less than 1. So certainly 1 is an element which satisfy that condition for an upper bound. Likewise, if you see, all the elements are greater than 0. So 0 is an element which is less than or equal to x for every x in my set A. So 0 is a lower bound. So that is the one which I have just written. 1 is an upper bound of the set A, 0 is a lower bound of the set A. Now, there are some natural questions which should come to your mind. Observe that these upper and lower bounds which we have just calculated are not an element of the original set. Does 0, 1 belongs to A? That I have asked you. I ask you to pause the video here and think it once. I think you have given a thought to it. 0 and 1 does not belong to my original set, but still they are upper and lower bounds. So from here we see that whenever we are going to find upper and lower bound for any non-empty subset of the real line, they need not belong to my original set always. So this is the observation which I made from this particular example, and this is true in general for any problem. The answer is no, surprisingly. A funny smiley for you. So in general, now this is the note which you should understand, that upper bound and lower bound for a set, of course non-empty, for a set, you should write better, for a non-empty set. For a non-empty set need not be a member of that set. Fine. So we are now almost reached to the final stage of our lecture. Now I'll be concluding with some important results before concluding this lecture today. You have to try to understand them. I'll explain it and try to prove it if it's possible. And if you get stuck again, then do post your doubts, whatever you have, in the Telegram group there, and you should try to solve them. That's what I want to say. Okay, let's see the first result, what it says. That if A is a non-empty subset of R and is finite. Finite means if you consider the cardinality of that set, that is, if you consider the cardinality of that set, then it has to be less than infinity. It has to be finite. Then in that case, this A will, the upper bound for that set will always belong to that set. You have to understand and prove this result. If your A is a finite set, there is some finite set on the real line, then its upper bound will always belong to that set. Now I gave you another question. Is it true whether the upper bound belongs to that set? What do you think for the lower bound? So try to solve for both the cases. Now let's see the second and final exercise for this lecture today. Any lower bound of any non-empty subset A of R is less than or equal to an upper bound. This is a very intuitive. Let me just draw a shape for you. It's very intuitive and easy exercise. You can visualize it. See. Suppose this is my real line. Let me just quickly sketch something for you, beautiful. This is my real line. Okay, perfect. Now let me choose my elements of the set. Suppose, as I have defined earlier, here and the union of, suppose, here, these, what this shows, all my small x, my elements of the set A lies here. These this and this both contributes to my set A, and these all are my small x, here also and here also, which belongs to my set A. And if now I try to fix an upper and lower bound for this set, try to see. You see this element somewhere here, let me call it I. By convention I am defining the upper bound to be alpha, so I denote by lower bound to be beta. Now an interesting fact and observation which you can see here, that my lower bound, this beta, is of course less than alpha. In this particular example, let's choose another example. Let's choose another example. Let me again draw the real line. In this case, let me just extend it. Yeah, perfect. Okay, let me just change the color. Okay. Suppose my set is non-empty, so I assume this time my set is a singleton. Suppose this 1, here my 0, and this is my set A. What is my set A now? A is the singleton one. In this case, if you see, you will find that 1 satisfies this condition, that 1 is less than equal to 1, because here this 1 is, I am considering my x, or you can just see it another way, then this 1 is a lower bound. Now if I see this x is less than equal to 1, this x is of course 1, this x is here, then this one is an upper bound. So in this case, if I call this lower bound by beta, if I call this upper bound by alpha, then of course my beta equals alpha. In this case, my beta equals alpha. So in the previous case, my beta was less than alpha. In this case, the beta is equal to alpha, but you will see geometrically and intuitively, it cannot happen that your beta surpass alpha, that your beta lies to the right of alpha if beta is a lower bound. That cannot happen. That will violate the definition of a lower bound then, if in context of upper bound, if you relate both the definitions. So from here, what we see, if beta is a lower bound, what I see, let me just conclude by writing that. Here I have written it. If my beta is a lower bound for my non-empty subset A, my alpha is an upper bound, then this hold always, that my lower bound will always be less than equal to the upper bound. Okay, so this was the final result of our today's lecture. I hope you got a good clarity, at least some basic idea of what is an upper bound, what is a lower bound, some good observations based on them. So try to solve each of the exercises given in the lecture, and feel free to ask me if you have any queries in the comment box, or maybe at the Telegram group. There it's better. Anything you find convenient. If you find this video to be useful and interesting, then do give us a like, and please do share about our initiative among your friends, so that they can also be equally benefited from the content which we are making. Thank you so much for watching, and we'll be meeting ahead soon in the next lecture with the concept of suprema and infima, and based on them some good interesting exercises from some good entrance examination. So thank you so much for watching.